who is a soon-to-be graduate student at UT Austin. She'll be leaving us pretty soon. And she's going to talk to us about NEID and building spectrographs to detect exoplanets. So here is Emily.
Okay, I build instruments, but I don't know how these work, so bear with me. Okay, my name is Emily. Thank you guys for the introduction. And I am here to talk to you about the great and ultra-stable spectrographs, NEID and HPF. I'm wearing the official team uniform, as you can see. So I'm going to tell you all about the spectrographs, but before I do, I want to talk to you a little bit about what is a spectrograph, why is it useful, why do we care? So in astronomy, most of our information comes from electromagnetic radiation, or light. There are a lot of different kinds of light, and you can kind of break them up into the different regimes in terms of wavelength. So the one that we're most familiar with is visible light, and it's the light that we see with our own eyes. But there are a lot of different kinds of light out there, including infrared. That's going to be important later. Don't forget. Spectrographs are useful to us as astronomers because they break up the light into their wavelength components. That's really important because that tells us a lot about the physical universe around us. That's also going to be important later. So when we look up into the night sky, we see stars. But if we could see in the infrared, we would see even more stars. So there are a lot of stars out there that emit in visible light and that emit in infrared light. That's also going to be important. So the way we build the spectrographs is defined by the science we're trying to do. And in exoplanet science, one of the big priorities is to find planets in the habitable zone. Habitable zone is where liquid water exists. It's not too hot, it's not too cold, so that's important. But what do I mean when I say Earth-like planets? So we're looking for planets in the habitable zone, but we want them to be Earth-like so that we can find life, because that's the ultimate goal, right, is to find life. So Earth-like planets, what does it actually mean? To know if a planet is Earth-like without actually going there and looking at it, we need to know about its density. And to know about a planet's density, we need to know about the size, the radius, and we need to know about the mass. So there are a lot of different ways we can learn about these two physical properties, but the main way that we learn about radius is with the transit method. Probably a lot of people here probably already know this, but the radius of a planet is proportional to the dip in light it creates when it passes in front of its host star. As you can see here, there's a bigger dip if the planet is bigger, smaller dip if the planet is smaller. That's all I'm going to say about that topic, but just to give you guys an idea. Mass information comes from spectroscopic observations instead of photometric observations. So in the transit technique, we're looking at photons, we're counting photons. And in the spectroscopic observations, we're taking a look at the spectrum of the light of the star that we're observing. This is called radial velocity measurements. Let me tell you a little more about that. So there's a lot going on here. Let me go through this step by step. The center of mass in this image is the common point around which the planet and the star are rotating. So the planet is rotating around the star, but actually they're both rotating around a common center of mass. This creates a wobble if you are looking at it in the plane of the orbit. So if there's an observer up here looking down, it's going to see that wobble. And the wobble manifests as a shift in the Doppler spectrum. So if you can see up here, this is shifting left to right as the planet goes around. The amount that it shifts is proportional to the mass of the planet. So we can back out these physical properties if we can project the spectrum and measure how much of a shift we can see. So it looks kind of like this. When we project the spectrum out onto a flat surface, we can see it moving, and that movement can be measured in this way. Whoa, that's going a lot faster than it's supposed to. But you guys get the idea. So we can get period out of this. We know the period of the planet. We know the mass of the planet, which is important. And we know the eccentricity of the orbit, so we can get a lot out of these observations. So you'll notice that this system is an M-dwarf system. An M-dwarf is a star that's much smaller than our own sun. So it's smaller and it's cooler, and there are a lot of them. So in that video I showed you before, where all of the infrared sources came onto the screen, there are tons and tons of these suns nearby, and if we can mine them for exoplanets, we may be able to find a lot of them. So if we want to find Earth-like planets, we also want to be looking at sun-like systems. Sun-like systems, the stars are bigger, they're hotter, but the problem is, if the sun is bigger, the shift is much smaller. It's much more subtle. So this is 1 meter a second. That's the speed at which it wobbles. And this is 10 meters a second. That's a whole order of magnitude smaller. That's really hard to detect, and I'm going to spend the rest of this talk telling you guys how hard that is to detect. So is everybody with me? Does everything make sense somewhat? Okay. You guys can ask questions later. So we need high precision spectrographs to see this centimeter per second shift. To give you an idea of how small this actually is, 10 centimeters a second, that shift, the shift of that spectrum, corresponds to 1/6000th of 1 pixel. You guys, the NEID detector is like this big, and it's 9,000 pixels by 9,000 pixels wide. So 1/6000th of 1 of those pixels is how big this shift is. So it's a really tiny shift, and we're very challenged to cut down all of the systematics in the instrument, and to take care of all the astrophysical noise that can look like these shifts in order to find the real signals. So this is a really big challenge. It's also really exciting. It's a multifaceted problem, so when you are looking at this level of precision, you need to take into account a lot of things. You have to take into account the telescope that the instrument is going on, the atmosphere, what's going on in the sky, barycentric correction, so you have to take into account how you are moving relative to the star that you're observing on the planet, because the planet is moving through space. Fibers, so this is a fiber-fed spectrograph. I don't actually have time to talk about this, but this is also a really interesting aspect of the spectrograph. Not all spectrographs are fiber-fed, but it means we're piping light from the telescope down to the instrument instead of sticking the instrument on the back of the telescope and having it move around with the telescope. Calibrators, we have to have really good calibration. Optics, I'm gonna show you guys pictures of the optics because it's just really cool. The optics are cool. Stability, I'm gonna tell you a lot about that. And the pipeline. So when we take the data, we need to be able to process the data very, very carefully. The 2 aspects of this project that I work on most are fibers and stability. There are a couple people in the audience also who work on fibers, a couple of the NEID people. Hey. But I'm only going to talk about stability today because I don't have time to tell you guys everything. We have a huge, huge team of people working on this project because it's such a challenge. This has really never been done at this level of precision before. So we have people at Penn State, all these people here, Irvine, Arizona, NOAO, Goddard, all these places. We need all these people because they're all experts in little things, and it all needs to come together perfectly. So now that I've talked your ear off about why and why it matters and why it's hard, these are the spectrographs. This is HPF. HPF stands for Habitable Zone Planet Finder. See, I told you habitable zone would be important. And NEID is over here. NEID is a Pima word, which means to see or to discover. Pima is the native language of the Tohono O'odham, on whose land Kitt Peak National Observatory is built, and we're privileged to be doing science there. Spoiler alert, NEID is going to Kitt Peak National Observatory. That's the connection there. You'll also notice that the spectrographs look pretty similar from the outside. HPF was built first, which is why HPF is on the front of the t-shirt. And NEID inherited a lot of HPF's design. So that's why we were able to build both of these here at Penn State. So let's return to this multifaceted problem. I'm going to tell you guys about environmental control system. This is how we stabilize the instrument. We need a perfectly thermomechanical stable instrument. And the ECS is how we do that. We designed the ECS to give us sub-millikelvin stability. That's just really, really careful thermal control. So spoiler alert, we were able to achieve sub-millikelvin stability. Thank you, yes. To give you an idea of what that means, what that actually looks like, this is a plot of temperature in the room. So this is the lab. This is where NEWID is right now. This gray line is the temperature fluctuations in the room. So they're huge. This box around NEWID here is the thermal enclosure. This is only half of it. It actually covers the whole instrument, but that's not a very interesting picture. So this is half of it. And that's that blue line. So inside the thermal enclosure, you still see fluctuations, but they're less. And then this red line is the optical bench. And the optical bench is the surface on which we put the optics in the heart of the instrument. And that's where we need the temperature control to be really, really good. So let's zoom in a little bit on this red line. We have, over the course of weeks, very, very, very stable instrument. Over the course of 10 days, we barely reach outside of 1 millikelvin, so 10 thousandths of kelvins. This is a very carefully controlled instrument, thermally. So thermomechanical stability is crucial. Here's schematics of the two instruments. You can see again how they look very similar. And they're kept at different temperatures, so they kind of complement each other. So remember how I said there are a lot of stars that emit infrared radiation. There are a lot of stars that emit visible light. HPF is designed to look at stars that emit infrared. HPF is kept at 180 Kelvin. That's negative 135 Fahrenheit. It's very cold. It's very cold in there. But it's in a vacuum chamber, so we don't have to wear coats when we go in there or anything. NEWID is for visible stars, stars that emit visible light. And NEWID is kept at 300 Kelvin, so that's about 80 degrees Fahrenheit. It's nice out, nice and warm. So you can see they're similar, but I'm going to talk more about NEWID specifically, because I've worked a lot more on NEWID, and I like NEWID more. Don't tell RPI I said that. So we maintain a vacuum in the instrument. We do this because we want to eliminate thermal gradients in the instrument in order to, by eliminating convection and radiation. That's how we maintain the sub-millikelvin stability that I've been talking about. Okay, so we're eliminating convection. There are two ways that you can transfer heat between two surfaces. You can have particles that are literally carrying that energy and physically bouncing from one to the other. That will transfer heat and create a thermal gradient. Or you can have radiation, so heat can radiate from one surface to the other. So we want to cut both of those out. The way that we eliminate convection is we eliminate the number of particles in the instrument. That's why we use a vacuum. So we have, down here at the bottom, liquid nitrogen tank. For nitrogen to be in liquid form, it needs to be very, very cold. So it's a very cold, cold tank. And we connect it to, oh, that's a pixelated picture. This is charcoal. You're gonna have to take my word on this. We connect the liquid nitrogen to charcoal and we cool the charcoal. The reason we use charcoal is because charcoal is very porous. We're maximizing kind of the amount of surface area that we can absorb particles onto by using charcoal. So we cool the charcoal. You know when you go outside, and it's a hot day, and you have cold water in your water bottle, and then you notice that water starts to kind of stick to the outside of your cold water bottle? It's kind of the same thing. The particles will stick to the cold surface of the charcoal, and they'll stay there. So if that's where the particles are, they're not floating around in the instrument, creating thermal gradients. Okay. So we've eliminated convection. We've eliminated all of these particles that are bouncing around, making problems. Now we need to eliminate radiation. And to do that, we use a multi-layer insulation blanket. So once we're able to get down and vacuum, get rid of all the particles, and then move this way with the insulation blankets and our active control, we get into the regime where we can detect these tiny, tiny movements without there being all sorts of systematics in the instrument. So let me tell you about the multi-layer insulation blankets. This is a picture of NEID. This is the radiation shield wrapped with an MLI blanket like a giant burrito. If you take one thing away from this talk, it's that NEID is a giant burrito. So when we take the MLI blanket off, this is the thermal radiation shield. Here's a better picture of it. You can see on the top, there are these 8 squares. These are Kapton heaters. So this is a schematic of the same thing. This is the radiation shield. There are 28 Kapton heaters all the way around the outside. Each one is a control station. So we are carefully controlling the temperature at all 28 locations on this shield. And we're controlling it very, very finely. So these are barely different temperatures. So this is across the whole surface. Let me talk a little bit about how we do that. This is the inside of the radiation shield. There are no optics on here yet. I'll show you guys the optics next. But at all 28 stations on the inside, we have sensors. The sensors tell the temperature monitoring control system how the temperature is changing at that location over time. The TMC uses a proportional integral derivative loop to do this. So it's basically just tracking changes over time. And then it routes power to the heater, depending on if the temperature is going down or if it's increasing, in order to maintain a set point. And again, we're doing this at 28 different locations around this whole box. So we are aggressively controlling the thermal gradients on the radiation shield. So this is what the bench looks like without any optics in it. And this is what it looks like with the optics. So I'm gonna show you some of the cooler optics, just because optics are cool, and I had never seen optics this big before in my life, before I started doing this project. But before I do that, I wanna talk to you guys about the light path through the instrument. So I'm gonna show you an animation, but I'm just gonna give you the overview first. Light comes into the instrument through a fiber. Remember I told you it was a fiber-fed spectrograph. So fiber pipes light into here. The light comes over to here to this parabolic mirror, over to the Echelle grating. Now the Echelle grating does sort of what the prism does, and it spreads the light out into a line, into its different wavelength components, like I talked about earlier. So now we have this line shooting through the instrument, comes back over to the parabola, over to the fold mirror, back to the parabola, to the prism, which then splays it in the opposite direction. So now we have a 2-dimensional footprint of light that we're going to be projecting onto the CCD to find those tiny, tiny RB shifts. So let me show you a video. I hope it'll play. Nope, didn't play. Hang on a second. There it is. So that's the light path. You can kind of also see some stray light happening, some light beams that are just not going where they're supposed to. That becomes a problem other times, but we won't talk about that today. It's a really big problem, you guys. So this is what the light's doing. So I'm going to show you guys the optics. This is the grating. It might just kind of look like a cool mirror, but it's actually 2 sections. We couldn't make a grating big enough for the instrument, so they had to make 2 and put them together. That was a bit of a challenge. It's made out of special glass. It's made out of Zero-Dur, which is good for optics. So that's the grating. The grating's okay. This is the parabola, the parabolic mirror on this side of the instrument that bounces light back that way. So the parabola has a very slight curve in this direction and in this direction. And when we got the parabola, we started playing with it. And when you move away from it, your image becomes magnified. So I walked as far away as I could. We were having a lot of fun that day. Making faces at you guys. Okay, so the parabola is really cool. And here's the prism. The prism is 130 pounds, hundreds of thousands of dollars, thousands of dollars. I don't think I'm supposed to say. Very expensive piece of glass. And it's coated with a very delicate optical coating. So when we moved it into its mount, we had to use a suction cup. It was the scariest 3 minutes of my life, hanging a very expensive giant brick of glass above nothing with a suction cup. But we did it. It's safely, which you guys remember. Talked a lot about HPF earlier, and then forgot about it. HPF is commissioned on the 10-meter HET telescope at McDonald Observatory. So our spectrographs have their homes, and I'm going to leave you with this kind of fun video of HPF being installed at HET, being pulled out of the truck and slowly, carefully shoved into the HET basement. And I will take questions now. Thank you.
What component inside of HPF is the biggest problem for, causes most of the stray light, I guess?
What component inside HPF causes the most stray light?
Yeah, or if there one exists.
So, I can't speak to HPF, but I can say stray light has been a problem for NEID recently. And we have found that certain surfaces that we didn't imagine in our wildest dreams would reflect light do. And so we have to be really careful about coating everything that's not meant to reflect light with, we've been using carbon nanotubes or Vanta Black, those very black paint. Yeah. So we have to go to far measures in order to keep things from reflecting light that are not supposed to. Because that is a big problem in the instrument. Yeah.
How much heat would you need to brew that?
Which instrument? The cold one?
Yeah.
Very little. Oh, right. How much heat would you need to ruin the instrument? Yeah, very little. Actually, while you're under vacuum, there's not a whole lot you can do. But when someone walks into the spectrograph room, into the HPF spectrograph room, we can tell because the bench will eventually see it. That thermal gradient will slowly print through, but not right away. So actually, it doesn't take very much.
It's probably not very much, but does the light that's coming through the spectrograph itself, if that's absorbed in the glass or whatever, does that then heat up the instrument at all? Does that have any kind of thermal effects?
No. Not that I know of. No, I'm seeing a shaking head from the grad students. No, that's not. The question is, when will NEID start taking data? I have stopped answering this question because when you're doing instruments, and actually I didn't mention this, NEID is an NSF NASA collaboration. So we are a NASA project, and we are on a very tight schedule, and things go very fast, and things slip. So when one part of the instrument slips, other things slip, and there's this snowball effect. So the deadline has been moving for quite some time now, but I think it will be before the end of 2019. 2019. What does my typical day look like? It's like the picture John showed of the woman screaming at the computer, but actually sometimes it's still a computer because we get the telemetry from NEID through the computer, so it's the same thing as John. No, actually I do a lot of really fun lab work. So one of the reasons I like instrumentation is because I get to build hardware. I get to be very involved in what's going on. I'm doing different things every day. So sometimes I'm working on wiring in the instrument to make sure that the environmental control system is working. Sometimes I'm working on fibers, so I'm polishing fibers, testing fibers in all these different ways. And again, I didn't really get time to tell you guys about that, but that's a whole other side of the project that's really interesting. So that's the general gist.
So, I guess the first thing that stands out for me when trying to build a more sensitive instrument would be the detector itself, because I'm guessing with your one figure, you show that you're going a blue shift and red shift of about 200 nanometers each direction, and with the 1 centimeter per second, you're probably not going as blue shifted and red shifted. So I'm assuming there's a lot of concern and thought being put into getting more sensitive detectors.
Yes, so the question is about detectors and how sensitive the detectors are. When I showed that whole list of things, the multifaceted problem, I didn't talk about the detector. There's a whole team of people at UPenn who are dedicated to the detector, testing the detector, characterizing it, so that we know exactly what to expect. Because yeah, different detectors are going to behave different ways. They're going to have different pixels that don't work. But I don't know a whole lot about that part of the project. So.
Why do you use a prism after the issue?
That's a good question. I don't have a good answer for that. Oh, yeah. The question is, why do you use a prism and not just another shell grating?
Well, another order, not necessarily an issue.
Yeah, so the short answer I can tell you is the prism is really efficient in throughput. So one of the things you want to measure when you're building a spectrograph is what's your throughput. How much light is going from the beginning to the end. And you can maximize that light by using different types of optics. But of course, there's a cost. So if you get good throughput, you may not get as good something else. So there are reasons, but I don't know all of them.
So since you have an active temperature control, is that going to put some limit on the lifetime of the instrument with respect to a passive one that would just sit there and do its job?
It's a good question. Since we have an active control system, since we have an active thermal monitoring control system, does that make the lifetime of the instrument less because it's not just passive and simple and has moving parts? Actually, it doesn't have moving parts. The nice thing about NEID, it has no moving parts. But I will say the lifetime might not be so different, but the maintenance itself over the lifetime is a lot more. So that is true. That's something we're seeing now, and that's a big part of my job is maintaining the wiring system is a lot because, right, there are 28 sensor monitoring control stations. Every control station has a heater and 2 sensors, and all of those have to not break. So things break, and so you have to do a lot of maintenance. Thank you, guys.